All right, next we have Gabe Conant. He's speaking about continuous stable regularity. Thank you, Gabe.
Thanks for coming, everybody. Thanks for online. Yeah, the talk is on continuous stable regularity. I was going to start by saying I was going to give you an example of continuous stable regularity. Then the next slide was just going to be the word stable regularity in very, very small font over and over and over and over again. Would have been a really funny joke. I'm glad I didn't do it though, because you're troubleshooting the slides, you would have seen it. Really the joke. So instead, I'll just start with the main definition of the talk, which is the notion of a stable function. So if you're familiar with stability and continuous logic, this will look familiar, but I'm hoping that the talk will have a good mix of model theory and combinatorial stuff. So depending on your interests. But right, so the definition, I'm going to start by looking at a function f from two sets v cross w to -1, 1 for now. I hope this isn't too confusing. The domain will change a little bit, but right now just a bounded domain is what we really care about. And v and w are arbitrary sets. And so then I'm going to say that this function is k delta stable, where k is an integer and delta is a real number, if you omit some kind of half-graph type situation, but where the values of the function are now important. So I'm going to draw this little picture. So I have my usual half-graph type picture, so maybe k equals 3 or something. So I omit a1 up through ak, b1 up through bk, and what do I not want to have happen? When I look at the value for any I less than j, if I look at the two values of the function across these diagonals, they're different by at least delta in absolute value. So it's kind of like this half-graph situation where I have this disagreement looking across the two ways of ordering the I and the j. All right, so that's the definition of a k delta stable function, and now this is going to make sense, of course, when v and w are finite as well, which will be kind of where we're going. I just want to say briefly, so a lot of people are really familiar now with the notion of a k-stable graph or formula in the discrete setting of just 0, 1 values. So I just want to compare that. It's slightly different, but close enough. So recall that the graph E bipartite say is k-stable if you don't have these a1 up through ak, b1 up through bk that give you an ordering. So this is sort of roughly equivalent to saying that the characteristic function of the relation E is stable in the previous sense, although you have to change the k a little bit because this definition doesn't decide which is which on the ordering, right? Whether you have an edge, the value of your function is 1, or if you have no edge, if the value of your function is 0, I haven't said which is which. So you have to change k with a Ramsey argument, but it's roughly equivalent to get all your colors to line up, right? So if I took if I looked at a different ij, which one's bigger and which one's smaller might switch. Okay, I hope that's kind of clear. It's not anything you really need to worry about. The only point is that up to a uniform change in the integer k, this is equivalent to the usual definition of k stability for a 0, 1 valued relation. Okay. So I'm going to start with some examples of stable functions because there's lots of nice examples. I mean, there are lots of nice examples of stable graphs as well. People are very familiar, but there's lots of kind of new examples of stable functions in a different mindsets, and a lot of them come from the setting of Hilbert spaces. So if some of the language is unfamiliar here, that's okay, because we're going to kind of simplify things down to very concrete examples. But for now, let H be a Hilbert space with unit ball U, and suppose I have some bipartition function phi on the unit ball into -1, 1, which is definable in the metric language for Hilbert spaces. If that's meaningful to you, great. If not, that's okay. The main example we're thinking about for the next couple slides is the inner product function. Okay, so that's the example to think about for here. But anyway, the point I want to make is that in this situation, for any delta, there is some k that depends only on delta and phi. In particular, does not depend on the Hilbert space, such that this function is k delta stable. And this essentially comes from the fact that as a continuous theory, the incomplete theory of Hilbert spaces is stable. Any completion of it is stable. I wasn't completely sure about the right reference for this. I think according to the current literature on continuous logic, it goes back to some work of Iovino, which was in this setting of Banach metric structures developed by Henson and Iovino. And then, okay, there's a stability proof there, and then it's kind of been recast in say, the monograph by Bernstein, Bennikov, Henson, Usviatsov as well. So you can look there for a different treatment of it. But at any rate, this gives us a nice way of constructing examples of stable functions in the following way. So now for the next couple slides, I'm just going to think of this inner product function. So k of delta is going to be the k of delta that comes if I'm only looking at the inner product. And so here's a corollary that appears in Hrushevsky's famous work on approximate groups, which is about kind of stability coming from Keisler measures and structures. So let M be an arbitrary L structure, now just classical logic for this. And then let mu be a Keisler measure on the definable sets. And then if I fix two formulas, so sorry, phi is now a discrete formula in this language, so phi xy and psi of xz, I can then define a function f from y space cross z space into 0, 1. Or what does it do? It takes two parameters a and b and gives the measure of the intersection of the two instances of these formulas. Oh, I'm sorry, I switched a and b to b and c. That's my bad. So this should be like a and b, a and b. Okay, so two parameters gives me two instances of the formula. I take their conjunction, I measure it, and that's the output of the function. This is now k of delta delta stable for all delta greater than 0, where once again, the point being that this k of delta depends only on the k depends only on delta. It does not depend on anything else. And so this is a particular, and now Hrushevsky's proof of this was different. I think this connection to the stability of the inner product in continuous logic is a more recent understanding. Hrushevsky proved this directly using some complicated tools, but this can be seen as a corollary of the previous thing where you consider your Hilbert space to be, so you think of your Keisler measure as a Borel measure on the type space, take L2 of that probability space, take the usual like integration inner product. Okay, you work it all out with the definitions or whatever, and then this function is precisely the inner product of these two formulas, but thinking of them as like characteristic functions on the type space. So it's exactly what it is. If you multiply two 0, 1 characteristic functions, you're taking the intersection of the sets that they are the characteristic function of. Okay, so at any rate, it's that example. And now for the audience that is less model theoretic and is more combinatorial, we can kind of recast this as giving examples in the finite case. All right. So again, the same k of delta. Here's now just a way to totally purely combinatorially build stable functions from finite sets. So you can forget about Hilbert spaces for this statement, but again, the proof is the same thing. So now let's just take x, v, and w to be arbitrary finite sets, whatever you like. I guess non-empty all the time. You should just always assume these things are okay. X, v, and w are arbitrary finite sets. Now take two arbitrary functions, g from x cross v into -1, 1, and h from x cross w into -1, 1. So these are arbitrary functions, whatever you want. Then I define a new function f from v cross w into -1, 1. And what do I do? So now I take, good, the a and the b are right. So I take an a and a b, an a from v and a b from w. If I think of those as like parameters, that gives me two fibers of this function g and h. And then what I've computed here is just the normalized inner product, but written out as a sum. So 1 over the size of x times the sum of the product of the two things. Okay.
Second line would be g, right?
No, everything should be right. So g goes from x cross v, h goes from x cross w, f goes from v cross w. So the a is from v goes here, b is from w. Yeah, so I'm basically just parameterizing two families of functions on x and then taking the inner product of those families with the parameters. Okay. So again, now these are stable functions where the k of delta depends only on delta, does not depend on the finite sets, the size of the finite sets, the functions you started with or whatever. So you can just generate stable functions this way. And it's the same proof, it's just a different Hilbert space. So this is now just the finite dimensional Hilbert space with this normalized inner product. And once again, that's all it is. Okay. Now I do want to say one thing, which is that this connection to Hrushevsky's work, and this corollary in particular about Keisler measures is an important part of his work on approximate groups. It was also used by Sergey and Conant to give a model theoretic type proof of Tau's algebraic regularity lemma, and then that inspired Tau to write a blog post where he gave a very simple kind of linear algebra proof of these kind of corollaries, where you can get some explicit information about how K depends on delta if you like. If you find that interesting. So there's actually a nice, for these, not the full generality statement, but for this kind of a corollary, like the previous one and this one, you can give real explicit linear algebra proof of this stability using something called Hilbert's inequality. Okay, and it's fairly elementary modulo some of these tools. Okay, so these are all for now examples. And the goal of our work, so I should have said at the beginning, this is joint with Conant, Pillay, and his student Nicolas Chavarria. I don't know if I said your last name right. I would just say, hey, you, right? Okay. So the goal of the project, and I kind of see this as the first step of a bigger project where we're like looking at continuous logic and these ideas of regularity that have been studied by a lot of people over the previous years. And so we started by asking the question of, well, what kind of analog of the Malliaris-Shelah stable regularity theorem for graphs can we prove in the setting of functions? And also, in addition to just getting a statement of that kind, we were also motivated by understanding, well, what kind of continuous logic development should happen to make this work. So there's a bit of interest in both, at least for me, is sort of the combinatorial side of what does the statement look like and what are its components, but also what's the underlying continuous model theory. Okay, so let me just state, okay, so I'm gonna state our result in a couple slides, but first I want to just recall the Malliaris-Shelah result. So now given a graph, a finite graph V, comma E, I wrote it for graphs, not bipartite graphs, because that's what's in their paper. I hope that's okay. But at any rate, given a graph, vertex set V, edge set E, and two subsets X and Y, and this is finite, we can define this edge density, so d sub E of xy, to just be the edge set intersect X times Y divided by the size of X times Y. So like the density of the edges between these two sets, you would usually maybe think of X and Y as being disjoint, but you don't have to. Okay, and so then a kind of cut down statement of what they prove is that if you have a graph that's K stable, so you can either use the usual definition I showed before, or you can think the characteristic function of E is K delta stable for any delta, if you like. At any rate, they prove that if the graph is K stable, then for any epsilon, I can find a partition of the vertex set into some number M pieces with a very good bound, such that for any pair of pieces, Vi and Vj, well, first, they're almost the same size, so their sizes differ by at most 1. And then 2, the density of the edges on the pair is either close to 0 or close to 1, so less than epsilon or at least 1 minus epsilon. Okay, so you break your graph into this bounded number of pieces, and then between each pair of pieces, the graph looks like nearly complete or nearly empty. So it's a very strong structure result for how the graph looks like. Of course, I've sort of decided to not go through the whole motivation for this using the Szemerédi regularity at the beginning, but many people are familiar at this point that a lot of the motivation for this was to give an improved version of Szemerédi's regularity lemma for specific graphs in which you have no irregular pairs and you have very good bounds, and stable graphs were the right setting for that. Okay. And then there's also a later proof of this by Malliaris and Pillay, using pseudo-finite methods that work at a kind of a more general setting of talking about Keisler measures on structures and stable formulas and stuff, but doesn't give equipartitions or explicit bounds due to the use of ultraproducts. And a key model theoretic tool in that work was this fact that any Keisler measure on a stable formula is a quote-unquote sum of types. So it's okay if you don't know what that means, but if you've heard of it before, we'll be talking about an analog in a couple of slides. Okay, so now, right, the goal then for us to get started was to prove an analog of this theorem for stable functions, and also kind of develop the same kind of underlying model theoretic tools as in the Malliaris-Pillay proof, but in the setting of continuous logic, which is an appropriate setting for talking about, like non-discrete valued functions, but like R valued functions, 0, 1 valued functions. Okay, so I'm going to state our main theorem first, but before that, I need to give you a definition that is going to mimic this idea of like 0, 1 density, but where we're using a function now instead of a graph. So there's a couple of different ways I think you could do this, and what we're kind of sticking to is the strongest way that emerged in our work. So the definition's not as terse as this with nice notation, but it gives a very complete description of the structure. So let me just show it to you, and I'm going to draw a picture. Okay, so now let's let f from v cross w to 0, 1 be a function with v and w finite sets. And yeah, I apologize for this. It's a little bit arbitrary, but now I'm going to really focus on 0, 1 valued functions for the rest of the talk. I think psychologically that's easier for people because continuous logic is often like done that way. But this is sort of really just a bounded interval is really the only important thing. Okay, so now this is the definition of what's called a homogeneous pair using a function. So I fix x and y, which are subsets of the two sides. So x is a subset of v, y is a subset of w, and I want to define what it means for this pair x, y to be kind of homogeneous for the function, which is supposed to be like almost all 0 or almost all 1 in the graph setting. But of course, it's more complicated now because you have more possible values for the function. So it's two conditions to make the definition symmetric, but what does it say? It says, well, I'm going to kind of unpack it. So it says that I can take some possibly smaller subset, say y prime. We'll do the same thing on the other side, but let me do this side for now. And y prime is, we haven't lost very much, so the size of y prime is at least 1 minus the second parameter gamma times the size of y. So if gamma is very small, this is almost all of y. And then the second condition says that if I take any point B in this slightly smaller set, I have this unique number R in 0, 1, so that if I look over here and I ask for the set of points over here so that the value of the function fxb is very close to this fixed number R. So it's within delta of R. So the squiggly delta means, or squiggly t means the absolute value of x minus y is at most t. Okay, so I've got a fixed R, a fixed delta. I take this slightly smaller set y prime, and I look at all of the things over here. I fix a point B in y prime. I look at all the things over here whose value under the function is very close to this fixed number R, where very close is measured by this parameter delta. And the conclusion is that this set is also almost all of x. It's at least a 1 minus gamma proportion of x. Okay, does that picture kind of make sense? Okay, and then there's a symmetric thing for the other side. I can shrink. Sorry? Yeah, so I'll say something about that. Yeah. Okay, right. So then there's a symmetric condition for the other side. If I shrink x by a little bit, fix a point in that smaller set, look at everything over here that's within delta of this fixed number s, that's almost all of the other side as well. Yeah. And so Sergey made the observation that, up to controlling these parameters, R and S should be close together. And you can indeed check that in the above definition. R and S have to be within, say, 2 delta plus 4 gamma. Okay. So that is just, that's just a calculation. But the idea here is, why do I have these two parameters? Well, we're going to see, as I state the theorem, that delta is going to be kind of like a fixed parameter connected to the stability of the function, and gamma is going to be an error parameter that I'm free to make as small as I want. So that's the reason I do want to have really two parameters here. This is going to be important. In practice, you should think of gamma as being much, much smaller than delta. Delta is kind of given to you because it's how stable your function is. And then gamma is just any small thing I want to pick. Yeah.
It should be a y, right?
Oh, there's so many. Yes, I'm sorry. This should be a y. This one should be a y. Yeah. Okay. But yeah, I mean, the picture is hopefully a little bit easier. Huh?
The picture made it clear.
The picture is better. Yeah. So, okay. Would have been good to put a picture on the slides, but I didn't. Okay. All right. So, okay. if your function were literally 0, 1, like 0 or 1 valued like a graph, this would just be saying that you have this kind of uniform, you have like almost all the edges are there or almost none of the edges are there. So you could compute a density bound similarly from this, but this is a little bit more precise and because it separates these two parameters, the delta and the gamma. Delta is how close to this fixed value R I want to be. That's going to be the stability parameter. And gamma is just how much little error I want to allow myself here. And that will be able to be chosen a little bit more strongly later on. Okay, so let me state the theorem then. So this is a theorem. So given an integer k, two real numbers delta and epsilon, and then a function sigma from the natural numbers to 0, 1. So this is my data given. I can find some bound n depending only on those parameters so that the following structure theorem for stable functions happens. So what does it say? It says, suppose that f from v cross w to 0, 1 is a k delta stable function on finite sets. So k and delta are the stability parameters. Then I can find partitions of the two sides. So v into v0 up through vm, w into w0 up through wn, where the number of pieces, m and n, are bounded by this bound capital N. And I have three things happen. So the first thing says that this is a little bit different from the Malliaris-Shelah result, but the first thing says that the v0 and the w0 are like small exceptional sets of vertices and small bounded by this global parameter epsilon. So I have these small vertex sets that I kind of ignore. And then if I look at the rest of them, the v1 up through vm and the w1 up through wn, they are of this, you have an equipartition of each side and exactly the same size. So vi, the size of vi equals the size of vj, and the size of wi equals the size of wj. And if I ignore the little v0 and w0 and I take a pair vi, vj among the rest, it has this strong homogeneity property where how close to the fixed value is it? It's 5 delta plus epsilon, which we'll kind of see why that appears in a minute. And then the error in the homogeneous pair, the error in how much I shrink these little sets is very, very well controlled by this function sigma. So this is like a new ingredient that maybe, okay, if you've only seen like the Malliaris-Shelah theorem, you wouldn't have seen it, but if you've been watching some of these other talks like Caroline's talk and Julia's talk, controlling the error with a function is a theme that comes up a lot. So we're actually controlling this little error in the homogeneous pair by some number that gets better and better and better the more pieces in the partition you have. Yeah, that's right. So Anand says there are 3 parameters around. I mean, really there's 4. The k is sort of less important. Really, it's the delta, epsilon, and the sigma that are important. But delta is the stability. Epsilon is a fixed global small error that I use to control these exceptional sets I have to throw away. And then the sigma function is this very, very, very strong control on the error in the homogeneous pairs. All right. So that's the statement. And right, so as a remark, when you do take the characteristic function of a graph, this does give like a qualitative strengthening of the previous formulations of stable graph regularity because we've put in this function. We're controlling the error with this function. Now you might say, well, why is that? Because before there were no v0 and w0. You didn't have these exceptional sets. Well, if you wanted to get rid of them, you could do it easily. You would just cut up the v0 and the w0 and distribute them evenly among the rest of the pieces. But that would destroy this strong homogeneity here. That would introduce epsilon into this second coordinate here. So you wouldn't have, and this is, I mean, I'm going to say a little bit more about why this controlling with the function is interesting. If you went to my course, I did a version of this in the graph case, and one way we saw that this sigma was helpful is that it easily lets you get an equipartition from a possibly unbalanced partition, much more easily than kind of other things that have appeared before. All right, and then I do want to say that in that particular graph case, where your function is actually the indicator function of a graph, there is a quantitative proof of this stronger statement in this recent work of Terry and Wolf that you've seen talks on recently. Okay, but in the function case, this is the statement we have now. Okay. Is there anything else I can say about it? Maybe just at a high level, I've partitioned V and W into these nice equal pieces, and then these small V0, W0 that I ignore. And then looking at pairs away from V0 and W0, I have homogeneity like this, where how close I am to this constant value R is being controlled by the delta parameter. And the error, though, how much I miss, how much I don't understand about what's happening in this homogeneous pair is very, very small, controlled by the function sigma. All right, so I'm going to say a little bit then about the continuous setting in which we give the proof of this. So I'm not going to give a whole tutorial on continuous logic. So if it's not your cup of tea or you're not familiar, you can just kind of sit back and enjoy some of the words or whatever. But all right, so let's let M be a metric L structure, and I'll just give some highlights. So just recall, this means that the universe of M is a complete metric space of bounded diameter instead of just an arbitrary set like in discrete logic. And then each L formula, instead of being like a 0-1 valued relation, it's now a function on the metric space, in fact, a uniformly continuous function into the real numbers with some bounded image that's like bounded in the language. So it doesn't, the image of the formula is bounded like the arity, it's independent of the structure. It's a part of the language. And so then in this setting, the collection of L formulas over the structure and some fixed tuple of variables X then becomes a vector space in the connectives that you allow for continuous logic. And it's not hard to check that it's dense in the set of continuous functions, the space of continuous functions from your type space into the reals. So there are these vector spaces. And then, right, and so then if you're familiar with the Malliaris-Pillay proof of the regularity, you know that it involves Keisler measures. And so here we need an analog of Keisler measures as well. How do you get a Keisler measure in continuous logic? Okay, in the discrete setting, you start with a probability measure on formulas, and then you go to a Borel measure on the type space. We can do the same thing here, but instead of starting with a probability measure on formulas, we start with a linear functional on the vector space of formulas. So in continuous logic, you could say a Keisler functional over the structure in your variables X is, say, a positive linear functional on the vector space of formulas of norm 1, which is reflecting like probability measure. Okay, you don't have to think about functionals for the talk. They're going to disappear right now, but they're there underlying the machinery, because using results from analysis, you can have a correspondence between Keisler functionals on formulas and the usual familiar regular Borel probability measures on the type space. So we're going to talk again about Borel measures on the type space, not about functionals. So it will hopefully be a little bit more familiar for people who are only working in discrete logic, but they come from this object on the formulas in a similar way. Yeah. Yes, so Anand raises a good point just to think in mind. This is the space of types, but S no longer stands for stone. It stands for types. I don't know. So yeah, in continuous logic, the type spaces are compact Hausdorff spaces, but they're no longer totally disconnected. All right. Okay, so the point of this slide is that I'm going to be talking about measures on type spaces, regular Borel probability measures on type spaces as usual. I'm not going to be talking about functionals, but I think it's helpful to know that they come from concrete objects on the formulas, just like in the classical case. Okay, more continuous logic settings. So now we're going to go to the local setting where I'm going to work around a single formula, which again, for simplicity, I'm assuming is 0-1 valued. So fix a 0-1 valued bipartition formula phi xy. We have the local type space, which can be constructed in a number of ways. So S phi m, and you have the same kind of behavior as in discrete logic. Any local type, any phi type is completely determined by how it behaves on instances of the formula. So this notation means what value does the type say that phi of xb takes, right? It's not 0 or 1 anymore, it's some real number. So some people would, I think if you look at the literature, this might be written like this instead. But okay, like the type contains information. What real number does it think this instance of phi takes? So I'm writing it as phi of pb, if that's okay. Well, you have your connectives there, but they're going to be determined by these. So like phi of xb plus phi of xc is going to be determined by phi of xb and phi of xc. So just like in a phi type in discrete logic, you don't, I mean, it's entirely determined by what instances of phi and their negations are in there. So is it 0 or 1 on every instance of phi? That determines all your conjunctions and disjunctions, etc. Same thing here. You just need to know the value of the type at every instance, and that will determine the whole thing. Okay, and then you can define a metric on this type space, which I've denoted d sub phi. And if I have two phi types p and q, it spits out the largest difference between any instance of phi. So the largest possible difference. So if this is 0, that's saying p and q agree on all instances of phi, so they're the same. But in general, this could be some other number, and you get a metric. And now you can, I know that, okay, if you're not used to thinking about this, it will be whatever, but you can start to think that if p and q are very close in this metric, then that's saying that they kind of agree on the fibers of this function. So you see this kind of regularity picture start to emerge, things being close together if they're in the same, or if they're a very small distance in this metric. Maybe it's worth saying that if you were looking at a discrete valued formula like 0, 1, this would just be the discrete metric. So types would be equal or not equal. But here it's a different kind of metric. And then if we pair these two things together, this compact Hausdorff space together with this metric, it's something that Benyakov, I think he invented this terminology, a topometric space. And there's a lot of nice things. There's a connection between the metric topology you get from this metric plus the compact Hausdorff topology you get on the space. Okay. So the study of topometric spaces is in a lot of the continuous logic literature. All right. And so then, yeah, there's some work here that already exists. So we can say that our formula is stable with respect to the theory of the structure if it's k delta stable for all delta greater than 0, or for all delta, there exists some k such that the function evaluated in this model is k delta stable. And then you can prove the usual kinds of things, that this is a property of the theory, not a property of the particular model you picked, and so on. Oh, yeah, Ward said earlier, they're right. Okay, thank you. Okay, and so then there's a paper by Benyakov and Usyetsov where they work out a lot of the local theory of stable formulas in continuous logic, including definability of types, the sort of error-co-error symmetry with definitions of types, and various things like that. And then there's another paper on kind of topometric spaces in general by Benyakov, where he looks at an analysis essentially of Keisler measures on type spaces when the formula is stable. So there's a lot of existing work on this, but to get the theorem that we wanted, we needed to rework some of this to get more approximate analogs, where instead of assuming that your formula is like k delta stable for all delta, it's just k delta stable for a fixed delta. So it's not fully stable in the sense of continuous logic, which kind of separates it from the existing literature a little bit. Okay, so we had to work through some things like that. And I think the next thing I'm going to show you is just kind of a very messy statement of what we proved upstairs about an arbitrary model. It's not the cleanest possible statement. Oh, no, I'm sorry. No, we're not there yet. Sorry. First thing I want to do is show you a cleaner statement, which is this analog of the result that says that a Keisler measure on a stable formula is a sum of types. So that was the first step, was to prove an analog of that. And so this is what it says. Assume that I have this formula, phi xy, in my continuous structure, which is just k delta stable for a fixed k and delta. Okay, fixed k and delta. And now let's suppose mu is a Keisler measure on the type space, by which I mean a Borel probability measure on S phi m, but it comes from a functional, but that doesn't appear explicitly in this statement. So let mu be a Keisler measure on this type space. Then, instead of writing it as a sum of types, I can write it as a sum of localizations on closed sets of very, very small diameter in that metric. So there are countably many pairwise disjoint closed sets, Ci, in the type space, such that the diameter with respect to that metric is at most 2 delta. And the measure then is the sum of, it's like a weighted sum, so alpha I times mu I, where alpha I is the measure of this little closed set Ci, and then mu I is just a localization of the measure on Ci. So the measure of a set. Do you know what I mean by localization? I'll write it. So mu I of a Borel set is mu of B just on the divided by mu Ci. So this is a new Keisler measure, and we're just weighting it that way. Okay, so that's the result. And then again, like in the discrete setting, if your formula were just like actually 0 or 1 valued, then as long as delta is less than 1/2 or something, then saying diameter less than 2 delta is just saying it's a single point, it's a single type. And so you get a weighted sum of types as in the usual case. But in this continuous case, it's little you're sort of concentrating on these little sets of bounded diameter all the way through. But this is okay for regularity, because now we're not getting in our homogeneity statement that the function is exactly equal to something. We're just getting that it's very close to something. And this is being reflected by going into these sets of very, very small diameter in a type space rather than single types themselves. Okay, yeah.
But what if we assume that it's stable with respect to the original definition always?
Yeah, so then you could say for any epsilon, I can find a sum like this, and I could write my function as being I could write my function as being kind of uniformly, or sorry, my measure as being kind of uniformly approximated by measures that concentrate on types again. But that doesn't really help with the regularity statement, because you still are going to have to give yourself a little bit of room. Okay, so this proof, I mean, it's, oh, yeah, almost sounded like a stream for a second, sorry. Interesting. Okay, so the proof is modeled after the kind of proof in discrete logic, but with some more topological tools. It uses this kind of approximate CB analysis, the so-called CB delta rank of a type space. I'm not going to say more about it, plus some other topological arguments. Okay, so that's kind of step 1 toward the thing, and then right now step 2. So this is what I was warning you about before. This is kind of then a fairly complicated statement about what's happening upstairs. So I'm going to draw a picture. So what kind of statement do we get about arbitrary stable formulas on arbitrary structures with arbitrary Keisler measures? Right. Okay, so I have my formula phi x, y. It's k delta stable for a fixed k and fixed delta. And now I have my type space S phi. So I'm going to write this as a statement where you partition the type space. It would be more natural to think about a partition of the model, but okay, that requires some delicacy I'm not going to say. And then I've got my other type space with the opposite formula. Okay, and then I have 2 Keisler measures. So mu is going to be a Keisler measure on this type space, and nu is going to be a Keisler measure on this type space, possibly different. And then now I have to fix some parameters. So for all epsilon greater than 0, there are going to be some bounds m and n, such that then for all possibly different gamma greater than 0, a bunch of stuff happens. And so this is reflecting the introduction of that control function sigma, where I have an epsilon that's global, but then I get an m and n after that, and then after that I can pick a gamma possibly depending on m and n. So this is where the function comes in. What does it say? I mean, you can read it, but it says, okay, I can find pairwise disjoint closed sets, V1 up through Vm, not saying a partition, and then pairwise disjoint closed sets W1 up through Wn. And then along with that, some phi star formulas, so formulas that are continuous combinations of instances of phi where I plug in parameters for x. And I have I'm going to draw them over here because I have one for each vi. So I call this zeta 1y up through zeta my. So these are continuous combinations of phi. And then the following happens. So one is that these pairwise disjoint closed sets take up almost the whole type space. So the measure of the union of these is at least 1 minus epsilon. So like the remainder, which is like acting like the V0, if you like, that has small measure. And then same thing over on the other side. The nu of the W1 up through Wn is at least 1 minus epsilon. And then I get something which is like a deconstructed homogeneity statement. First one says that if I look at a VI and I take any point over here, B, in the m to the y side, and I look inside this little piece, let's say V1 here, I look at what's the set of elements where the value of the formula, so if this is an A and this is B now fixed B here. I look at where is that within 3 delta for various reasons of what this associated phi star formula thinks if I plug in B, so this would be zeta 1 of B. Okay. So first I just look not at a fixed value on the right, but this function kind of only depending on the V. And then the first thing says, well, that's almost everything. Almost, this picture's now really hard to read, sorry. V, oops. V1, A, and then I look at this set of things like this. The first thing says that that set in mu measure is almost all of the VI with this even better gamma here. So this even possibly smaller gamma. Okay. Now that doesn't look like homogeneity because this could possibly change as I change B, this value. So this is kind of the analog of a good set in the Malliaris-Shelah terminology. But then the second or the third condition says that if I look at a VI and a VJ, this function actually doesn't change very much. So I'm not going to draw the picture. But for all I and j, there is some unique number r in 0, 1, so that if I look, okay, I'll draw the picture a little bit, but if I look in wj now, I have this unique number r, and I ask, well, what's the set of things in here, b, where zeta I of b is within 2 delta for various reasons of this number r, which now depends on I and j, and that says that that's almost everything also. So put those two things together and you get a 5 delta. You have like something that's acting like a homogeneous pair. Okay. So yeah, and then there's a symmetric condition I didn't write for the other side, but this is a first approximation to the kind of main theorem for stable formulas and arbitrary structures. We clean that up a bit. We have to deal with these closed sets and start talking about things that are given more by formulas and stuff, move it into the model. And then there's, of course, a whole pseudo-finite argument to actually get the finite statement, which requires some new delicacies. I think this is an interesting kind of thing to kind of clean up this area of doing these kinds of pseudo-finite regularity arguments in continuous logic. There's some stuff that was a bit tricky to work out. Okay, so yeah.
How does it relate to the 2 values, R and S? What is the...
Yeah, I'm sorry. So I did, because of this is already messy enough, there would then be a symmetric statement with an S going the other way as well. You would have other formulas associated to these pairs and do the symmetric thing. So yeah, I should have maybe made that more clear, but it's already kind of messy enough. Okay. All right, so then in the last few minutes, we did start a little late, but in the last few minutes, I wanted to say some words about, so this will be back to the combinatorial setting, if anybody's stuck with it, if you haven't been interested in the model theory statements. But back to the combinatorial setting of this kind of analytic form of regularity for functions. So a natural question, if you're thinking about the idea that the Malliaris-Shelah stable regularity lemma is supposed to give some kind of an improvement on Szemerédi's regularity lemma for graphs in the setting of stable graphs, you might then, of course, ask, well, what's the function analog of just a general Szemerédi's regularity lemma that this could possibly be improving, this stable case? So I wanted to say a little bit about that. So we need some terminology. So let X be a finite set, and we already talked about this normalized inner product on functions from X to R. It's just it's the usual like inner product. You multiply F and G together, but I'm normalizing all the time. Okay. And then from this inner product, you get the L2 norm, but now normalized, but in the same way. And then the infinity norm will also show up. So I'll just remind you the sort of uniform or sup norm is just the largest absolute value that the function takes. And it's very easy to check that you have an inequality that way. Yeah, so these are norms on the vector space of real valued functions on X. X will later be a V cross W, but there's no need to complicate that now. Okay. Right, so to state kind of the Szemerédi regularity for functions, we need some definitions. So fix an arbitrary function f from V cross W. Now we're back to -1, 1 again. I'll say a little bit about that. So we've got a notion of being structured and a notion of being random. So we say that the function is structured with parameters m and n if I can partition my two sets V and W into m pieces for V, okay, m plus 1, and sorry, that should be an n that should be, where the hand is an n. So I partition W into n+1 pieces, and then on each pair, the function is constant. So it's like an indicator function of boxes, Vi cross Wj. Sorry? No, so here yeah, I mean, yeah, don't think of V0 and W0 as being exceptional sets now anymore. That'll come up later. Hopefully I'll get time to finish it. Okay. Okay, so that I think is sort of a natural thing, just indicator functions of boxes and then linear combinations of those. What is the randomness notion? So you say that the function is epsilon pseudo-random if whenever I take the indicator function of an x cross y for any x and any y and take the inner product with f, I get something with very small absolute value at most epsilon. So you have to like work with this notion to appreciate it, I guess. But the idea is that if you're familiar with the idea of a pair xy being epsilon regular for some graph E with a particular density, say D, then that corresponds to saying that the function where you take the characteristic function of, sorry, it's not x and y, it's v and w. I'm sorry, v and w. So if your pair VW was epsilon regular for a graph in the usual way with some edge density D, then that's corresponding to saying that the indicator function of the graph minus this density D is epsilon regular, but you might have to change this to like a 2 epsilon or an epsilon squared or something like that. Sorry, epsilon pseudo-random. Okay, so this pseudo-randomness notion, the terminology is from a paper by Tao, but it's supposed to capture the idea of regularity for graphs. Okay, and then Szemerédi's regularity lemma for functions states that if I take an epsilon, I take a function sigma, I can find some bound n depending only on that stuff, so that if I take an arbitrary function, v cross w, to 0, 1, then I can decompose it into 3 ingredients, 3 parts. So the first part is a structured part. It's structured for some m and n bounded by n. The second part says that is a pseudo-random part, and it's extremely pseudo-random. It's not just epsilon pseudo-random, but it's sigma of mn pseudo-random. So the pseudo-randomness is very, very well controlled by a function. And then finally, the error thing just has small norm. Okay. So if you're thinking of graphs, this is representing like the partition. This is representing all of the regular pairs. And this is representing essentially the, like irregular pairs with some tweaks. Okay. So I'm going to have to rush this, and I apologize, but fortunately Henry is giving a talk this afternoon. There is some work here from last year of Chernikov and Tausner where they do this kind of a decomposition for a continuous notion of NIP. Maybe I won't read it because I don't want to run out of time too much, but they give there is a result like this that you can glean from their work, but I should say that the focus of their work is really on higher arity functions of this bounded VCN dimension in higher area. They weren't really focusing on the NIP case, so you might be able to clean the statement up in that setting. But essentially what it says is that if you have an NIP function in continuous logic, where it's, and the NIP definition is now for all delta, it's like for all delta there is a K so that your function is NIP, then you can break it up into a structured piece and an error piece. So the pseudo-random term goes away. But now what I want to say about the stable situation is that it's really difficult to say precisely what happens to a stable function using only norms. The norm, somehow just these norms, the L2 norm, the infinity norm, the pseudo-randomness is also associated to a norm. These don't really tell you exactly what's happening with a stable function. What's really going on with stable functions is that there are ingredients that are based on functions with very, very small support, okay? And it's really kind of about looking at the supports of these functions. So some last bit of terminology before I say the finite thing. Suppose x is a finite set, fix any function, say from x is -1, 1. Then just an easy observation to make is that if the size of the support of the function, by which I mean where the function's non-zero, if the size of the support of the function is very small, like at most epsilon times the size of x, well then you can think of it either as an error thing or as a pseudo-random thing, sort of trivially. It both has small norm and the inner product with any function is small. So, okay, so functions of small support can be kind of thought of as you wish by either being like small error things of little norm or by like very, very pseudo-random things just because the support's small. And so that's kind of what's going on in the setting of stability. And so for the next one's the last slide, I'm just going to use this notation. The ds is density of the support of F is just the size of the support divided by the size of its domain. And so now I can state kind of this functional decomposition corollary of our work. For any k, for any epsilon delta, same parameters as before, for any function sigma, there's some bound n, depending only on those, so that if I take an arbitrary k delta stable function from v cross w to 0, 1, then really what happens is there's 4 components happening. So F naturally breaks into 4 pieces. The first is a structured piece, so that same structured piece of bounded complexity. And then there's this uniformly bounded fluctuation from the delta. So bounded in the infinity norm. You can move by 5 delta plus epsilon, which is natural. And then the other 2 terms are these terms that you can either think of as being error terms or pseudo-random terms, depending on how you want, because they both have very, very small supports. The first one, which really comes from, I've called it the pseudo-random term because it kind of analogously comes from that same place. The density of its support is extremely small, at most sigma of mn. So very, very small density. But I can't really say the shape of the support of this function. It could be all over the place. It's very small, but it could be all over the place. The last one, the error term, it also has small support, which isn't quite as small because it's in terms of epsilon, but I can tell you exactly what its shape is. It's just these nice boxes coming from the exceptional sets V0 and W0. It's not, it's like really some kind of one-dimensional thing, not a two-dimensional thing in some sense.
So F times what?
Yeah, so, right, so the F error is, I don't want to restrict to this because that would be changing the domain. I want to think about it as a function on the domain V and W, but I multiply by the indicator function of this. So it acts like F on this support, and then it's 0 everywhere else. But the point is that its support, I can say exactly what it is. It's just built from these boxes. It's not all over the place. Okay, so depending on how you like, you can then combine things together. You could put these 2 things together into one function of small density, but then the epsilon goes back in. So that corresponds to, if you want to get rid of the V0 and the W0, you have to allow epsilon. And then if you don't like this little fluctuation, you could put them all together and they still have small norm, but now bounded in terms of everything. So you can kind of play around with it as you wish, but really I think that this way of stating it is the right way. A structured piece, a small fluctuation from the delta stability, a very, very small supported function, and then a very well-structured small supported function. Okay, and then that's the end. Thanks for your patience.
All right, we have a few minutes, couple minutes for questions. Are there questions from the audience? Or online?
So I just so in the situation that we only have the structure part and the fluctuation part, how does such a function look like? Would it look like almost a piecewise constant function, and there's some error?
Yeah, so I mean that's the idea. Is it's like an indicator function that's constant all the time, but then you allow a little bit of error, and this is a very natural thing to do because, I mean, if you have a function f which is uniformly bounded by say some delta, it never gets value more than delta, then it's trivially delta stable. No values. You can't find an order property that's separated by delta because the function never even goes past delta. So it makes sense that if you're talking about delta stable functions for a fixed delta, that you'd have to allow some fixed uniform fluctuation in your picture because it's there. I mean, okay, there's a 5 delta that appears because of how the actual structure thing comes, but up to changing the parameters, fixing the infinity norm at some delta makes sense because that's going to force delta stability just from trivial reasons.
Thanks.
I guess I have a naive question, but so in the case where I guess f is just like a characteristic function, and instead of taking like in the continuous setting, instead of taking sizes of your sets, you take like say, you know, finite measure. Like, was there already some sort of like Lebesgue density theorem, but for Keisler measures? Like, what do you recover that, or was that already something that existed for Keisler measures?
I don't know if I understand.
Well,
what you mean by,
Lebesgue
like, the
density measure meaning like when you zoom in enough, everything either has like locally measure 1 or locally measure 0. Like, was this already a thing for?
So I think if you're referring to the theorem about like writing the Keisler measure as a sum of things that are
Yeah.
concentrated on small sets, yeah. So anything you can say about that in the continuous setting, if you went to the discrete setting of the 0, 1 valued, which is what you're asking about, right?
I guess, well, I was thinking like for characteristic functions, this is much simpler than arbitrary functions. Wondered.
Yeah. So in that case, it would be you would just be able to do the same proof as in the discrete setting to say that the measure is a sum of types.
Hmm.
So it would look exactly like that.
Are there other questions from the audience? All right, let's thank Gabe again.
Thank you.